The water drips from a small hole at the base of a clay vessel, falling into a lower bowl in the lamplight of an Egyptian temple, and the sound it makes is neither urgent nor slow. It is simply steady. The vessel is shaped like a truncated cone, wider at the top than the bottom, its walls angling inward as they descend, and the interior surface has been worked smooth, then marked at intervals with lines cut carefully into the clay. Each line represents an hour. Each drip represents a portion of one. The lamp that lights the room is oil burning and low, and the shadows it throws across the vessel's walls make the graduation marks look deeper than they are, as though time itself had pressed them there. This kind of vessel is called a clepsydra. The word comes from Greek meaning water thief, though the Egyptians who built these instruments had no Greek word for what they were doing. They were simply trying to hold time in place long enough to measure it. What they understood, through long observation and practical correction, was that water does not drain from a vessel at a constant rate. A full vessel pushes its water out with more pressure than a vessel that is nearly empty. The flow speeds at the start and slows as the water level drops. A cylindrical container, measured honestly, would tell the wrong time. The hours at the beginning of the day marked too close together, the hours near the end too far apart. The engineers who built these instruments had no equations for fluid dynamics and no word for hydraulic pressure. What they had was patience and a willingness to look carefully at what the water was actually doing. The solution they arrived at was the shape itself. By tapering the walls outward from bottom to top, making the vessel narrower where the water was deepest and wider where it was shallow, they created a geometry that partially offset the falling pressure. As the water level dropped and the pressure decreased, there was proportionally less water remaining to exit, and the widening walls meant that each unit of depth contained more volume near the top, slowing the apparent fall. The compensation was not perfect. No clay vessel, hand-shaped and hand-marked, could achieve perfect compensation. But across a single-use cycle, from full to empty, from one marking of the hours to the next, the error was small enough to be useful, small enough to organize a temple's rituals, to coordinate the changing of a night watch, to track the movements of priests who had duties timed to the sky. The oldest surviving Egyptian clepsydra date to roughly 1400 BCE, though the practice of water timekeeping in the region is thought to be considerably older. The vessel found in the Temple of Karnak, attributed to the reign of Amenhotep III, shows not one set of hour markings, but 12, one for each month of the year. The Egyptians understood that the length of an hour, as measured by sunlight, varied across the seasons, that a summer day was longer than a winter one, and that a system built for June would be wrong in December. The clepsydra at Karnak was built to hold all 12 versions of the hour simultaneously, its interior walls inscribed with a different set of graduations for each month, arranged so that the priest attending the clock needed only to know which set of marks to read. That is not a primitive instrument. That is an instrument designed by someone who had thought carefully about the relationship between water and time, between the fixed vessel and the changing sky. The lamp burns. The drip continues. In the lower bowl, the water that has fallen through the night catches what light there is and holds it quietly on its surface. By the time the bowl is full and the upper vessel empty, another portion of measured time has passed, and someone, a priest, a scribe, a temple official whose name has not survived, will tilt the upper vessel, pour the water back, and begin again. Roughly 1,000 miles to the northwest, and 2,000 years before the Karnak clepsydra was carved, a different effort to hold time was already well underway. On the Salisbury Plain in what is now southern England, A structure was taking shape across centuries of labor, its builders moving stones from distances that by the engineering available to them should not have been possible. The monument we call Stonehenge was not built at once. Its construction unfolded in phases across roughly 1,500 years, from approximately 3000 BCE to 1500 BCE, the effort spanning more generations than the entire history of recorded European literature. Each phase added to or adjusted the structure that previous generations had left, meaning that no single person who worked at Stonehenge ever saw the thing that all of them together were building. What the finished monument preserves, or what survives in its ruined state to preserve, is an alignment. Standing at the center of the main circle and looking outward along the monument's central axis on the morning of the summer solstice, the eye is drawn toward a rough sandstone pillar that stands alone just outside the main ring. This stone is called the heel stone. It is not dressed and shaped like the large sarsen lintels of the inner circle. It is a natural boulder, pitted and rounded by weathering, its surface pale gray in ordinary light and a deeper amber when wet. It stands about 9 meters tall at its highest surviving point, leaning slightly toward the circle, and on the morning of the midsummer solstice, viewed from the monument's center, the sun rises precisely above it. Precisely is a word worth pausing on. The alignment is not approximate in the way that a guess is approximate. The heel stone's position was selected, or confirmed, or adjusted through some process of observation and correction that left it exactly where the rising solstice sun would frame it when seen from the center. Researchers studying the monument's geometry have noted that the original alignment may have involved a now missing second stone, and that the sun's disk, at the moment of solstice, rises such that the heel stone catches its light at the earliest possible instant, before it clears the horizon. This is not an accident of a roughly north-facing structure. The axis of Stonehenge is oriented to within fractions of a degree of the true solstice azimuth, a precision that required either repeated observation across many years, a sophisticated oral tradition for transmitting measurement, or both. The people who accomplished this had no theodolites and no written records of what they were building toward. They had ropes and stakes and the accumulated observations of many generations of sky watching. They had apparently a capacity for long-term collective intention that allowed a project begun by one group of people to be continued, corrected, and completed by their descendants in a form that the original builders never lived to see. The solstice sunrise at Stonehenge, when the sky is clear and the light comes in low and horizontal across the open plain, catches the heel stone's rough surface and lights it from one side before anything else in the landscape is lit. For a few minutes on that one morning, the stone glows, and then the sun climbs and the alignment passes, and the stone goes back to being a large rock standing in a field. It waits, as it has waited for 4,000 years, for the same morning to come around again. South and east of the Salisbury Plain, in the river valleys of Mesopotamia, a different civilization was developing its own relationship with time, one that was less monumental and more systematic, built not from stone, but from numbers. The Babylonians, who inherited much of their mathematical tradition from the earlier Sumerians, organized their numerical thinking around a base that was different from the one most modern cultures use. Where a base 10 system counts in groups of 10, the Babylonian system counted in groups of 60. This is called a sexagesimal system, and the reasons for its adoption are not entirely settled among historians of mathematics, but one compelling observation is simply this: 60 is divisible by 12 different whole numbers. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60 itself, all divide into 60 without a remainder. This makes 60 extraordinarily useful for anyone who needs to divide things into equal parts, and the people who needed to divide the circle and the day into equal parts were, precisely, astronomers and timekeepers. The Babylonian astronomical tradition was meticulous and cumulative. Priests and scholars tracked the movements of the visible planets across decades and centuries, recording their observations on clay tablets in the wedge-shaped marks of cuneiform script. One group of such tablets, known as the MUL, a pin collection, records the rising and setting times of fixed stars and planets across a span of observations extending back at least to the early first millennium BCE. The tablets also record the division of the day and night into equal units, and those units are the direct ancestors of the hours, minutes, and seconds still in use today. The Babylonians divided the day into 12 double hours, and each double hour into 60 minutes, and each minute into 60 seconds, and this structure, 60 minutes to the hour, 60 seconds to the minute, passed through Greek astronomy into the Roman world, and eventually into every clock and watch and phone display that has ever shown a time since. The clay that preserves this legacy is fragile. Many tablets crumbled before they could be read. Many were destroyed in the fires that consumed the libraries of ancient Mesopotamia, or scattered by the conflicts that ended the Babylonian state. What survives is a fraction of what existed, and what existed was the product of a tradition that understood the sky as a source of order, that saw, in the movements of Jupiter and Saturn and Venus, a regularity that human life could be organized around. When a Babylonian astronomer sat down with a fresh tablet and a reed stylus and began recording the position of Jupiter across a series of successive nights, arranging the numbers in columns of 60, he was doing the same thing the Egyptian engineer did when he shaped his clepsydra as a truncated cone. He was trying to hold time in place long enough to understand it. He was trying to make measurement reliable in a world where everything moved and nothing stayed still. Across the Atlantic, separated from the Babylonian world by an ocean that would not be crossed for another 15 centuries, a different civilization was approaching the same problem from a different angle and arriving at a solution of extraordinary ambition. The Maya, who developed one of the most sophisticated intellectual cultures of the ancient world independently of any contact with the civilizations of the Eastern Hemisphere, constructed a calendrical system that tracked not just the cycle of days and years, but an unbroken linear count of time stretching backward to a mythological origin point. This system is called the long count calendar, and it measures time in units that build upon each other in a sequence that works, in its basic structure, something like a very large odometer. The smallest unit is the kin, a single day. 20 kins make a unal. 18 unals make a ton, a period of 360 days approximating a year. 20 tons make a katon, and 20 katons make a bakton, a period of 144,000 days, roughly 394 years. The long count calendar tracks time as a position within this accumulating count, written as a series of 5 numbers that function like the digits on a counter. A date in the long count is expressed as the number of elapsed baktons, katons, tons, unals, and kin since the calendar's origin point, a mythological moment of creation that scholars of Mesoamerican calendrics have correlated through the complicated process of aligning the Maya calendar with the European Gregorian calendar to approximately August 11th, 3114 BCE. That origin date lies more than 5,000 years in the past from the present day. The Maya scribes who inscribed long count dates on stone stelae in the first millennium CE were counting forward from a point more than 3,000 years before they were born. They were writing numbers that located their own present moment within a sweep of time so long that even their own mythological history barely extended back to its beginning. The long count calendar is in this sense one of the most ambitious linear timekeeping systems ever devised by a pre-industrial civilization. A system designed not merely to track the agricultural cycle or the religious festival calendar, but to locate any moment in human experience within a continuous, unbroken count of days stretching from the origin of the world to its eventual end. The Mayan scribe who carved a long count date into a limestone stela was pressing more than a calendar entry into the stone. He was making a claim about where this particular moment stood in relation to the entire span of time, and in the process, he was building an archive. The stelae that survive, those that have not been destroyed or lost or worn beyond legibility, still carry those numbers. They can still be read, and when the count that runs from the mythological creation date of August 11th, 3114 BCE is extended forward through the inscribed dates of classic Maya civilization and onward to the present, the continuity holds. The days still add up. The long count has not been interrupted by the passage of time. It has simply continued, silently, whether or not anyone has been attending to it. Between the flowing systematum of the Babylonian tablets and the carved permanence of the Maya stelae, something else was happening in the Mediterranean world, a crisis of timekeeping that built slowly over centuries before becoming, in a single year, unavoidable. The Roman calendar, in its republican form, was a lunar calendar that had been repeatedly adjusted, patched, and modified in ways that accumulated error rather than correcting it. The calendar was nominally the responsibility of the Pontifex Maximus and the College of Priests, who had the authority to insert intercalary months, additional days, added to realign the calendar with the solar year. In practice, this authority had been exercised inconsistently, often for political rather than astronomical reasons. Magistrates who wanted a favorable year extended it. Those who wanted a rival's term shortened contracted the calendar. The result, by the middle of the 1st century BCE, was a calendar that had drifted significantly from the actual position of the seasons. Julius Caesar, returning from his campaigns in Egypt in 46 BCE, brought with him a Greek astronomer named Sosigenes of Alexandria and a plan. The Julian calendar that Sosigenes helped design was a solar calendar of 365 days, with a leap year of 366 days, added every 4 years to compensate for the approximately quarter day, by which the solar year exceeds 365 days. It was a considerable improvement over what it replaced. But before the new system could begin, the old one had to be brought back into alignment with reality. The Roman calendar in 46 BCE was running approximately 3 months ahead of the astronomical seasons. The calendar said autumn, while the weather said summer. The calendar said winter, while the harvest was still coming in. Correcting this required something drastic. Caesar and Sosigenes inserted 2 additional intercalary periods into 46 BCE, alongside the one already scheduled by the traditional calendar, extending the year to a total of 45 days. No Roman alive had ever experienced a year that long. The months that were supposed to arrive in autumn did not arrive until winter. The festivals that marked particular moments in the agricultural cycle fell on dates that no longer corresponded to those moments. The year simply continued past the point where any previous year had ended, stretching forward into a territory that had no precedent, adding days that did not appear on any existing calendar and had no established character or ritual association. Romans called it the Annus Confusions, the year of confusion. The name was not entirely unkind. It acknowledged the strangeness of the situation, while also acknowledging that the strangeness was temporary, that when this extended, disordered year finally ended, what came next would be more reliable than anything that had preceded it. The administrative burden of managing an extended year fell to the priests and officials who maintained the public calendar, the fasti, the inscribed or painted record of days, their religious status, their associated festivals, and legal designations. The men who worked with this record in 46 BCE were adding to a document that had, in some form, been maintained continuously for centuries. They were adding days that had no historical precedent, no accumulated meaning, no tradition attached to them. The days simply had to exist in order for the following year to begin in the right place. The priests marked them, assigned them their legal designations, dies fasti, dies nefasti, days on which courts could or could not sit, and moved forward, day by day, through a year that no living Roman had been born in time to prepare for. The calendar extended. There is something in this that is worth sitting with for a moment. The Roman state, at the height of its power and sophistication, with its legal system and its engineering, and its military reach extending across 3 continents, had to stop and admit that time had gotten away from it. Not through ignorance. The astronomers of the ancient world understood the solar year well enough to correct for it, but through the accumulated consequences of small decisions made across many generations for reasons that had nothing to do with astronomy. Political convenience for priestly authority, the ordinary human tendency to delay uncomfortable adjustments until they become unavoidable, these had built up across centuries into a 3-month gap between the calendar and the sky, and the only way to close that gap was to live through 445 days of a year that everyone understood was wrong in order to arrive at a year that would finally be right. The fasti were amended, the intercalary days were added, the priests continued their work, and somewhere in Rome, in the autumn of a year that should have been winter, or perhaps the winter of a year that should have been spring, the exact moment is not recorded. An official dipped a brush in pigment, or pressed a stylus into wax, and added another day to a scroll that had already gone further than anyone expected. Not with ceremony, not with particular complaint, simply because that was what the calendar required, and the calendar, however confused, still had to be kept. The water clock in the Egyptian temple also had to be kept. When the upper vessel ran dry and the lower bowl was full, someone had to pour the water back. The process had to begin again. The stone at Stonehenge had to be there when the solstice came, and it was, and it still is. The Babylonian scribe had to fill another column of numbers, extend the count another night. The Mayan stonecutter had to press the count of days into the limestone and let it harden. Every system of time that human beings have ever built has required this kind of maintenance, the steady, unheroic work of keeping the measurement going, of checking the mark against the water level, of adding the intercalary day, of carving the next date in the sequence, even when the sequence stretches back further than memory and forward further than imagination. None of these instruments were perfect. The clepsydra's taper compensated for falling pressure, but could not eliminate the error entirely. The calendar of the Pontifex Maximus could not survive the politics it was embedded in. The long count calendar required a correlation constant to be linked to the Gregorian calendar, and scholars still debate which constant is correct. Stonehenge, whatever its precise alignment, has lost the stones that may have completed its geometry, and we're left reading the intention from what remains. These imperfections are not failures. They are the evidence of genuine work, of people who understood that time moved, that it needed to be tracked, and that tracking it was difficult enough to require ingenuity rather than merely effort. A truncated cone, a sandstone pillar on an open plain, a column of 60 numbers pressed into wet clay, an unbroken count of days extending back beyond the beginning of recorded history, a calendar scroll that kept extending day by day until it reached 4:45 and stopped. These are not failed attempts at something better. They are the best that could be done with what was known, and what was known was, in every case, more than a casual observer might expect. The Egyptian engineer who chose the cone understood fluid dynamics without having a name for it. The people who placed the heelstone understood solstice astronomy without a written tradition to preserve their calculations. The Babylonian scribes understood the relationship between large divisible numbers and reliable measurement. The Mayan long count is a feat of intellectual ambition that has no obvious equivalent in any other pre-industrial calendar system anywhere in the world, and the Roman priests who added those final unprecedented days to the annus confusion is understood something that all of the others understood too, that the work of keeping time is never finished, that the calendar is always, in some sense, running slightly behind or slightly ahead of the sky, that the gap between the instrument and the thing it measures is a permanent condition, not a temporary embarrassment, and that the only honest response to it is to keep measuring, keep correcting, keep extending the scroll to whatever length the year requires. Even if that length has never been reached before, even if no one alive has experience of what that length feels like from the inside. The priests of Rome in 46 BCE added their intercalary days to a document that was already crowded with history, pressed their marks into the wax or the stone, or whatever surface the fasti of that year were maintained on, and moved forward. The year ended, it always does. Even 445 days will eventually run out. When it did, the new calendar began, and the months fell where the seasons actually were, and the confusion that had accumulated across generations was not erased, because nothing accumulated across generations is ever entirely erased, but corrected, at least for now, at least close enough to be useful, close enough to organize a temple, coordinate a watch, mark the moment of a solstice, count the days back to the beginning of the world, close enough in the honest, imperfect, endlessly maintained way that all timekeeping has always been, close enough to do what timekeeping is for. The lamp in the Egyptian temple burns low by the time the upper vessel has emptied. The lower bowl is full. The water on its surface holds the lamplight in a flat, still pool, and the room is quiet except for the last few drops falling from the hole at the base of the cone, each one slower than the one before, as the pressure finally fails and the flow gives out. A priest or a student of the priest's craft, or perhaps only a servant assigned to this task and no other, lifts the upper vessel and tilts it, and the water that has measured the night's hours flows back to where it began. The graduated walls of the cone, now empty, catch the light again. The marks are still there. They were always there. In a few moments the vessel will be full again, and the drip will resume, and another portion of time will begin its slow passage toward the lower bowl. Outside, the sky over the Nile is beginning to change. The deepest dark of the night is giving way, very slowly, to something that is not yet light, but is no longer entirely darkness. The stars that were directly overhead an hour ago have shifted westward, the whole vault of the sky, turning as it always turns, indifferent to the vessel in the temple and the marks on its walls and the priests who tend it. The sky does not require timekeeping. Only human beings require timekeeping. Only human beings look at the turning sky and feel the need to translate its motion into something they can hold in their hands, something with marks on it, something that can be read and corrected and passed from one generation to the next. Even the builders of empires, in the end, found that the sky outpaced their calendars. They added their intercalary days, extended their scrolls, lived through the long, strange year of confusion, and arrived, eventually, at a calendar that fit the world a little better than the one before it. The water dripped, the stone waited, the numerals accumulated in their columns of 60, the count of days pressed forward from its mythological beginning, and somewhere in a city that no longer exists, a priest dipped his instrument into wet clay one more time and added one more mark to a record that would outlast him by 2,000 years, still legible, still counting, still holding the shape of an hour that someone long ago decided was worth measuring. High in the upper atmosphere, roughly 15 kilometers above the ground, a particle arrives from somewhere outside the solar system. It enters at very nearly the speed of light, and when it collides with an air molecule, it produces, among other things, a muon, a particle, something like an electron, but heavier, unstable, and in ordinary circumstances, very short-lived. At rest, a muon decays in about 2 microseconds. That is not very long. At the speed it is traveling, the muon should disintegrate long before it reaches the ground, consumed by its own brief internal clock somewhere high in the stratosphere, its existence ending without ever touching the surface of the earth. And yet the muon arrives. It is detected at sea level, in instruments on the ground, in numbers that should not be possible if the only clock in question were the one written into its own physics. Something has happened to the interval between its formation and its decay. The time available to it has stretched, not metaphorically, not as a matter of perspective, but in a way that instruments measure and equations describe, and no other explanation has ever satisfactorily replaced. The muon lives longer because it is moving fast, and because it is moving fast, time for the muon runs differently than it runs for the air and the ground and the instruments waiting below. This is not a small effect buried in the margins of a theory. It is the kind of thing that changes what a person thinks time actually is. Albert Einstein published the special theory of relativity in 1905, and embedded inside it was a claim that seemed almost too clean to be describing reality. A clock in motion runs slow, not because motion damages the mechanism, not because vibration disturbs the oscillation, but because time itself, for an object moving through space, proceeds at a different rate than it does for an object at rest. The mathematics were exact. At 10% of the speed of light, the effect is small but detectable. At 90% of the speed of light, a clock ticks at only 44% of the rate of a stationary one. More than half its time is gone, not lost to error or friction, but genuinely, measurably absent from the interval the moving clock experiences. The equation sits there quietly in the theory, and for a while the theory was trusted because of what it predicted about light and electromagnetism, not because anyone had yet tested the clock-slowing piece directly. The muons, when physicists eventually looked carefully at their decay rates in particle accelerators and in the atmosphere, were the confirmation. Particles accelerated to near light speed in laboratory settings live measurably, provably longer than their slower counterparts. The discrepancy matches the formula. It is not approximate. It is not within a loose margin. The numbers agree to the precision the instruments allow, and when the instruments improve, the agreement holds. There is something restful about this. The equations were written before the instruments existed to test them at that scale, and then the instruments caught up, and the equations held. The universe, in this instance, did exactly what the mathematics said it would. What makes the muon particularly good to sit with is its concreteness. It is not a thought experiment or a hypothetical clock in an imagined spacecraft. It is a real particle, produced constantly by real cosmic rays, falling through real air, arriving at real detectors where real physicists record its presence. Every muon that reaches sea level is a small demonstration that time bends under velocity. There are thousands of them arriving every minute. A muon passed through the space above the room just now, or close enough to now that the distinction does not matter. The effect that slows a clock because of its velocity is only one version of the phenomenon. There is another version, equally exact, equally confirmed, that has to do not with motion, but with gravity. Mass curves space, and curved space affects the rate at which time passes. Clocks that sit deeper in a gravitational field, closer to large masses, lower to the ground, run slightly slower than clocks positioned higher up, farther from the source of the gravity. The effect is tiny at human scales, but it is real, and modern instruments are sensitive enough to see it. In 2010, a group of physicists at the National Institute of Standards and Technology in Boulder, Colorado, placed two atomic clocks on a laboratory bench. These were aluminum ion clocks, among the most precise timekeeping instruments ever built, accurate enough that they would not lose or gain a single second over the span of several 100 million years. The physicists then raised one clock 33 centimeters above the other, not 33 meters, not 3 kilometers, 33 centimeters, roughly the distance from a tabletop to the bottom of a hanging shelf. They waited, and they measured, and the two clocks diverged. The higher clock ran faster than the lower one, not by a dramatic amount. The difference was in the range of 4 parts in 10 to the 17th power, which is a number so small that writing it out would require placing a decimal point, followed by 16 zeros before the relevant digit. But the divergence was real, and it was consistent, and it was exactly what Einstein's general theory of relativity had said it would be nearly a century before the instrument capable of measuring it existed. The fact that this can be demonstrated on a laboratory bench with two clocks and a stack of books is worth staying with. The effect does not require black holes or neutron stars or the crushing gravity near a collapsed sun. It is happening right now, between the floor and the ceiling of any room, between sea level and the top of a hill, between the basement and the roof. It is the kind of thing that is everywhere once the measurement is fine enough to find it. The same effect that is barely visible across a bookshelf becomes at larger scales a significant engineering problem. Somewhere above the Earth at this moment, roughly 20,000 kilometers up, well out of the atmosphere, following circular orbits at several kilometers per second. There are satellites whose entire function depends on knowing exactly what time it is. Each one carries an atomic clock. Each one broadcasts a precise timestamp. The navigation systems on the ground that use these satellites work by comparing the arrival times of signals from multiple satellites and calculating position from the differences. The accuracy of the position fix depends directly on the accuracy of the timestamps. Errors in the timestamps become errors in location. The satellites are moving fast. Because they are moving fast, their clocks run slow. The same effect that extended the muon's lifespan, working on a mechanical clock at orbital velocity. At the speeds these satellites travel, their clocks lose approximately 7 microseconds per day, compared to a clock on the ground. 7 microseconds is not very much time, but signal errors of that size accumulate, and in the context of a positioning system, they translate into location errors of roughly 2 kilometers per day. A navigator using GPS that did not correct for velocity-based time dilation would find their calculated position drifting further from reality with every passing hour. The satellites are also higher up, because they are farther from Earth's gravitational field than a ground-based clock. Their clocks run fast. The elevation effect seen on the laboratory bench amplified over a much greater difference in altitude. At 20,000 kilometers, this effect adds approximately 45 microseconds per day in the opposite direction from the velocity effect. The net result is a daily gain of roughly 38 microseconds. Uncorrected, this would accumulate into position errors of several kilometers per day, growing steadily, making the whole system progressively less useful until it became useless. The engineers who designed the GPS system knew this. The relativistic corrections are not an afterthought or a patch applied after something went wrong. They are built into the fundamental architecture. The clocks in the satellites are manufactured to run at a slightly different base rate than ground clocks, tuned in advance to compensate for the relativistic effects they will experience once in orbit. When a GPS satellite is on the ground before launch, its clock runs slightly slow compared to ground-based reference clocks. Once it reaches orbit, the combination of velocity and altitude brings it into near-perfect synchronization with the systems below. The adjustment is precise, and it works. Every time a phone locates itself on a map, it is using data shaped in part by the mathematics Einstein wrote at his desk in Bern in 1905. There is a quality to this that is worth noticing. The Ewing relativity is sometimes described as a theory of extreme conditions, particles near the speed of light, gravity near a black hole, phenomena that have nothing to do with the ordinary world. But it turns out to be embedded in devices that fit in a pocket and tell a person where to get off the train. The laboratory confirmation and the satellite correction are both products of instruments measuring very small intervals very precisely. What happens when a physicist decides to remove the precision instruments and simply get on a plane? In October of 1971, a physicist named Joseph Hafele and an astronomer named Richard Keating arranged to do exactly that. They had with them 4 cesium atomic clocks, the most accurate portable timekeeping devices available at the time. Cesium clocks work by counting the oscillations of cesium atoms exposed to microwave radiation, and they were accurate enough for what Hafele and Keating needed. The plan was simple in its audacity. They would carry the clocks around the world on commercial airliners, once flying east and once flying west, and then compare the traveling clocks to reference clocks that had remained at the United States Naval Observatory in Washington. The eastward journey and the westward journey were not equivalent. The Earth rotates eastward, and a plane flying east is adding its velocity to the rotation of the planet beneath it, while a plane flying west is moving against the rotation. The velocity effects on the onboard clocks would therefore be different for the 2 flights. The altitude effect, because both flights occurred at roughly the same elevation, would be roughly the same. Einstein's equations, when applied to the specific routes and durations Hafele and Keating had planned, predicted specific clock differences, not just a general direction, but actual numbers in nanoseconds for each flight. Hafele sat with the cesium clocks in the cabin of a commercial airliner. He bought them tickets, or more precisely, he bought them seat assignments, because the clocks needed to be secured in their cases on adjacent seats and not stowed in the cargo hold where they might not survive the journey intact. The records from the flight include the faintly comic detail of a physicist sharing an armrest with a device the size of a carry-on bag, one of the most precise clocks in the world, on its way around the Earth to test a theory that nobody had tested at this scale before. After the eastward flight, the clocks had lost approximately 59 nanoseconds compared to the Naval Observatory reference clocks. After the westward flight, they had gained approximately 273 nanoseconds. The predicted values, worked out in advance from Einstein's equations, were 59 nanoseconds lost and 275 nanoseconds gained. The agreement was within experimental uncertainty for both flights. The equations again held. It is worth sitting with the numbers a moment. 59 nanoseconds is 59 billionths of a second. 273 nanoseconds is less than 3/10,000ths of a millisecond. These are not intervals that any human being can perceive or feel or notice, but the clocks noticed, and the equations predicted the noticing in advance, and there is something quietly satisfying about that chain. A theory, a prediction, a journey, a comparison, a match. The atomic clocks on commercial airliners were confirming in the macro world what the muons had been demonstrating since long before anyone was looking for it. Moving objects experience time differently from stationary ones. The difference is small at the speeds available to airplanes and small at the altitudes of navigation satellites, but it is measurable and it compounds over time, and the universe does not make exceptions for convenience. There is a different kind of time experiment that takes place not in aircraft or orbital paths, but inside a human being, in the particular compressed interval of a moment of fear. The experience is familiar enough that it has become a kind of common knowledge. The sense that during an accident or a fall or the sudden arrival of danger, time extends, slows, stretches out into something longer and more detailed than an ordinary moment of the same clock duration. People who have been in car accidents, who have fallen from heights, who have narrowly avoided something, often describe this. The moment felt slow. They saw everything very clearly. They had time to notice things they would not normally have noticed. The explanation most people reach for is neurological. The brain, under threat, speeds up, the processing accelerates. More is computed per unit time, more is perceived per second, and the result is a subjective experience of the world moving more slowly. The way that a fast motion camera, running at a higher frame rate than normal, will produce footage that plays back at what appears to be a slowed down rate. This is an appealing explanation. It is also, as it turns out, not what happens. David Eagleman, a neuroscientist then at Baylor College of Medicine, and his colleagues designed an experiment to test whether the brain genuinely processes information faster during perceived time dilation. The test device was a wrist-mounted display that could flash numbers at a rate fast enough to exceed normal human perception. The numbers changed too quickly for a person at rest to read them under ordinary circumstances. The idea was this: if the brain truly accelerates its processing during fear, then a person in a state of genuine acute fear should be able to read numbers that would normally be invisible to them. Their enhanced processing rate would make the previously unreadable readable. The method of inducing fear was not subtle. Participants were dropped from a platform 150 feet above a net. The fall took several seconds, long enough for the fear to register fully, for the experience of time to dilate in the way the participants consistently described. Afterward, they wore the number display on their wrist and were instructed to try to read it as they fell. Nobody could. The numbers moved too fast under free fall, just as they had under ordinary conditions. The brain's processing rate did not increase during the fear state. The numbers remained unreadable. What changed was not the speed of perception, but something that happened afterward, in the consolidation of the memory. The amygdala, a structure in the brain involved in threat response, signals the formation of particularly dense memories during moments of fear and danger. More detail is encoded, more sensory information is retained, more of the moment is stored. When that memory is later retrieved, the density of information makes the interval feel longer than a comparably brief interval from an ordinary moment, which leaves fewer traces. The brain interprets its own recording as evidence of duration. A rich memory feels like a long experience, even when the clock says otherwise. This is a piece of knowledge that seems modest at first and turns out to be larger on reflection. The felt length of a moment is not a simple function of what the clock measured. It is shaped by how much was saved, how much was written down by the part of the brain that decides what matters. Moments under threat are written down in detail. Moments of routine pass without much of a record. Later, the detailed moments feel long and the routine ones feel brief, and the result is a subjective sense of time that does not correspond cleanly to the objective one. The people who fell from the platform and felt time slow were right. In a sense, their experience of the interval was genuinely longer than their experience of comparable intervals from ordinary days. They were just wrong about the mechanism. The slowing was not happening in the fall. It was happening in the remembering. What Eagleman's experiment found, and what the Hafele-Keating clocks found, and what the Naval Observatory's reference standards confirm day after day, is that time is a more varied and flexible thing than the word suggests. The word implies regularity, uniformity, a constant background against which events occur, but the background is not constant. It bends under speed, it deepens under gravity, it lengthens in memory under threat. It is registered differently by a clock on the ground and a clock in orbit and a brain in freefall. The differences are small at human scales, in most cases too small to notice without instruments of extraordinary precision, but they are not zero. The cesium clocks Hafele and Keating carried around the world were among the most expensive, most carefully maintained, most precisely calibrated instruments in their era. The difference they detected was 59 nanoseconds. The NIST physicists, who raised one clock 13 inches higher than the other, waited a long time to accumulate a measurable divergence from a starting difference of 4 parts in 10 to the 17th. These are the smallest slices of time that physics has yet learned to see. And in those slices, the structure of the universe is visible. There is something grounding about this. The physics is extreme in the sense that the numbers are very small and the instruments are very precise, but the phenomenon itself is not confined to extreme situations. It is happening to every object moving through space, at every altitude, at every speed. It is happening to a clock left on a table and to a clock carried up a flight of stairs. It is happening to the particles in a beam at a particle accelerator and to the ones falling through the sky above. It is happening continuously, everywhere, at scales that matter in GPS receivers and particle detectors and nowhere else in ordinary experience, but present nonetheless. The muon that fell from the upper atmosphere and arrived at the ground, alive past the point its own physics should have allowed, was not doing anything unusual for a muon. It was simply moving fast in a universe where moving fast stretches the time available to a thing. The cesium clocks on the airplane, gaining and losing fractions of a second nobody could feel, were doing what every clock does when it moves and changes altitude. The satellite, tuned to run slow before launch so it would run right once in orbit, is doing now what it was designed to do, keeping correct time in a relativistic universe. one correction built into another. Hafele and Keating returned from their flights, collected their data, brought their clocks back to the Naval Observatory, and made their comparison. The numbers came back close enough to the prediction that the physics community accepted the result. Someone had gotten on a plane with the most accurate portable clocks in the world and flown around the Earth to check whether Einstein's equations held at that scale. The equations held. The clocks came back slightly different from the ones that stayed home, in exactly the right direction, by nearly exactly the right amount. The care involved in that confirmation has its own particular quality. It would have been possible to simply trust the mathematics. The theory had passed enough tests by 1971 that very few physicists doubted it in principle. But Hafele and Keating wanted to see the numbers, to hold the clocks, to make the comparison and look at it directly. There is something in that impulse that is completely distinct from the mathematics. The equations are abstract. The cesium clock in its case, on the seat beside Hafele, was not abstract. It was a thing traveling east over the Atlantic in the dark, ticking slightly slower than the one it had left behind. The confirmation that emerged from those flights was not a surprise to the physicists involved, or to the wider community. What it was, and what it remains, is a demonstration, not just that the theory is correct, but that the correct theory is the kind of thing that can be carried in a bag onto a commercial flight and confirmed with careful weighting and a comparison afterward. The universe's stranger properties do not hide in conditions unavailable to investigation. They are measurable. They were measured. They go on being measured every day in orbiting satellites and underground detectors and laboratory benches where two perfect clocks sit a bookshelf apart, counting time at rates that differ by an amount smaller than any word for small that ordinary language has. The muon arrives. The satellite corrects its clock. The physicist on the plane waits. The clocks come back slightly different, and the difference is exactly what was predicted, and the world goes on exactly as it did before, with a somewhat fuller picture of what it is doing. In 1956, a geochemist named Claire Cameron Patterson held a fragment of the Canyon Diablo meteorite under the light of his laboratory and prepared to measure something that no one had measured before. The meteorite itself was not a graceful object. It was pitted and dense, its skin a mixture of iron and nickel that had traveled through open space for billions of years before striking the Arizona desert with enough force to carve a crater nearly a mile wide, and its surface carried the texture of a thing that had been through something enormous and emerged still intact. Patterson was not thinking about the crater. He was thinking about lead, specifically about the ratio of particular lead isotopes locked inside the meteorite's ancient metal, a ratio that, if the equations held, would tell him exactly how old the solar system was. It took Patterson years to get those measurements clean. The lead contamination in his laboratory was severe enough to throw off every early reading, and the effort to eliminate it required building one of the first ultra-clean laboratory environments in scientific history. What he found when the numbers finally settled was that the Canyon Diablo meteorite was approximately 455 billion years old, and that Earth, having formed from the same original cloud of material, was roughly the same age, 4.5 billion years. The number existed in the literature before Patterson's work, but not with precision, not with the confidence that comes from a measurement made carefully enough to trust. Patterson gave the Earth an age the way a careful observer gives a name to something that was always there, not creating the fact, but making it possible to hold. That number, 54 billion years, sits at the center of everything that follows from it, and the mind does not easily find a way to feel it from the inside. 4.5 billion years does not compress naturally into anything a human life has prepared anyone to understand. The most honest approach is to find the edges of it, the oldest things that have survived to be examined, the events early enough to have shaped everything that came after, and to let the distances between them gradually become real. The oldest solid material found on Earth's surface is a crystal. Not a large one, it is a grain of zircon, no larger than a particle of coarse sand, pulled from the Jack Hills of Western Australia, and it has been dated to approximately 4 billion years old. Zircon is a mineral that forms at high temperatures and locks certain elements inside its crystal structure so efficiently that the ratio of uranium to lead it contains does not change, except through the predictable mechanics of radioactive decay. This makes a zircon crystal something like a sealed record, not written, but chemical, carrying the signature of the conditions in which it formed with a fidelity that persists across geological time. The Jack Hills grain formed when the Earth was barely 100 million years old. The crust beneath it was still thin and unstable, and much of the planet's surface may still have been partially molten. The oceans, if they existed at all, had only just begun, and yet this grain formed and survived and was eventually carried by erosion into sediment, where it rested undisturbed through the entirety of what followed. Through every ice age, every continental rearrangement, every extinction and emergence, until a geologist in the late 20th century collected it and a physicist counted its atoms. Holding that grain alongside the meteorite Patterson examined, both of them artifacts of the same early solar system, one arriving from space and one formed inside the cooling rock of early Earth, it becomes possible to sense that the planet's first 100 million years were themselves a kind of deep time within deep time. Things were happening at speeds that have since slowed enormously. Crests were forming and breaking, oceans were accumulating, and approximately 5 billion years ago, near the very beginning of all of this, something struck the Earth at an angle and velocity that would determine the shape of every night sky that ever followed. The body is called Theia, and the name is the only graceful thing about the event the name belongs to. By the current best understanding of the moon's origin, a hypothesis supported by isotope analyses of rocks returned by the Apollo missions, Theia was roughly the size of Mars, and it struck the proto-Earth at a glancing angle rather than head-on, which matters enormously. A direct impact at that scale would have been purely destructive. A glancing impact vaporized portions of both bodies and flung an enormous volume of molten rock and gas into Earth's orbit in a pattern that was not quite stable, not quite dispersed, a broad ring of debris that over hundreds of thousands of years began to pull itself together under its own gravity. The material cooled as it contracted, it rounded, it settled, it became the moon. The Apollo rocks that confirmed this hypothesis did so by revealing an unexpected closeness. The oxygen isotope ratios in moon rocks and Earth rocks are nearly identical, more similar than Earth rocks are to meteorites from Mars or the asteroid belt. If the moon had formed elsewhere and been captured by Earth's gravity, those ratios would differ. They do not differ. The moon is in a meaningful chemical sense made of the same material as the Earth, rearranged by an impact old enough that the solar system was still completing its own formation when it happened. Every tide that has ever moved water on this planet, every full moon that has ever risen over a forest or a field or an ocean traces back to that collision in the first 100 million years of everything. The sun formed before all of this, before Earth, before the impact, before the moon. It is approximately 6 billion years old, which makes it slightly older than the planet orbiting it, born from the same original cloud of gas and dust that collapsed under its own gravity into a dense hot core where hydrogen nuclei began to fuse into helium. That fusion process has been running continuously for 6 billion years. It runs now. Every photon of sunlight that reaches Earth in any given moment is the product of nuclear reactions happening inside a star older than the planet it illuminates, and that star, by the best current estimates, has used roughly half of the hydrogen available to it in its core. The Sun has approximately 5 billion years remaining in its current form. In that time, it will continue much as it is now, a yellow dwarf burning steadily, too hot and bright for comfort if examined closely, unremarkable by the standards of the galaxy it belongs to, but stable in a way that has permitted, among other things, the entire history of life on Earth. When the core hydrogen is finally exhausted, an event billions of years distant, the Sun will expand. Its outer layers will grow outward past the orbits of the inner planets, and it will become what astronomers call a red giant, wide and diffuse and cool at its surface compared to the dense hot star it is now. Eventually, its outer layers will drift away entirely, leaving the dense remnant of the core to cool slowly over trillions of years into a white dwarf, a dense object about the size of the Earth, radiating the last of its stored heat into the dark. None of this presses closely, because 5 billion years is a longer reach forward than the age of the Earth is a reach back, and the Earth's entire history is already beyond the range of anything that feels personally urgent. These timescales belong to the register of cosmology, the kind of fact that sits quietly in the mind, wide and undisturbing, like a view across a plain so large that the far edge is not actually visible, but is assumed, out there, in the direction the land continues. What does press slightly closer, though still at a considerable distance, is the history of life on Earth's surface. Non-avian dinosaurs, the great reptilian lineages that dominated the terrestrial world before the end Cretaceous extinction, existed for somewhere between 165 and 175 million years. That span of time is long enough that it contains within itself distances comparable to the ones people tend to find most dramatic. The early Triassic sauropods, the long-necked herbivores moving through landscapes that would be barely recognizable today, were separated from Tyrannosaurus rex by a gap in time greater than the gap that separates T-Rex from human beings living now. The dinosaurs were not one thing, uniform across their era. They were a succession of worlds, each one descended from the last, spanning a duration so long that the earliest and the latest were as remote from one another as the Cretaceous is from the present. A sauropod in the Triassic period, moving through low ferns in the late afternoon, would have had no experience of, and no imaginable connection to, the predators that would eventually come to define the popular image of the Mesozoic. The world it moved through was wetter in some regions, drier in others, warm without the polar ice caps that exist today, populated by creatures mostly gone from the modern record. And then, across roughly 160 million years of slow change, through dozens of climate shifts, through the slow repositioning of continents, through the rise and fall of countless species, the lineage of large theropods eventually produced the animal whose remains would be found in South Dakota and Montana and Wyoming, the one whose skull is large enough that a person can stand inside the reconstructed jaws. Between those two animals, the sauropod and the rex, stretches more time than separates the rex from us. That fact tends to rearrange something quietly in the way the Mesozoic feels. It is easy to think of dinosaurs as a single chapter, a coherent episode with a beginning and an end. They were closer to a library, hundreds of chapters, each one long by any human standard, the whole thing spanning a duration that makes the entire record of human civilization look like a marginal note scrawled quickly at the very back. It is, in fact, very nearly this small. Carl Sagan introduced the cosmic calendar in 1980 as part of his television series Cosmos, as a device for making the scale of time available to ordinary imagination. The conceit is simple. If the entire age of the universe, 8 billion years, is compressed into a single calendar year, each month represents slightly more than a billion years, each day represents roughly 38 million years, and each second represents approximately 438 years. The universe on this calendar begins at midnight on the 1st of January. The Milky Way forms in mid-May. The Sun and Earth do not appear until early September. The first simple life on Earth emerges in late September, early October. Complex multicellular life, animals with body plans recognizable to a modern eye, does not appear until mid-December. The dinosaurs arrive on December 25th and are gone by December 29th. The earliest members of the genus Homo appear in the final hours of December 31st, and all of recorded human history, every city, every dynasty, every war, every piece of music ever written down, every scientific discovery, every surviving building, occupies the last 10 seconds of December 31st. 10 seconds. From the first agriculture to the space telescope, from the earliest cuneiform tablets to the present moment, the total span of organized human civilization on Sagan's calendar is less time than it takes to say goodnight. The pyramids at Giza appear in roughly the last 7 seconds. Rome rises and falls in the last 5. The printing press appears in the last second. The Industrial Revolution, the germ theory of disease, powered flight, the discovery of DNA, the sequencing of the genome, all of it in the final second, crowded into a moment too brief to fully observe before it is already the past. There is something in this that is not alarming, but is very quiet. The calendar does not diminish human history. 10 seconds of real time is not trivial, and the density of what has happened in those 10 seconds is extraordinary by any standard that can be applied to life on Earth. What the calendar does is locate human history accurately within the full sweep of what came before it, and what came before it is genuinely enormous. The universe was constructing stars and destroying them for 9 billion years before the sun formed. Life was working its way through bacteria and algae and jellyfish and trilobites for hundreds of millions of years before anything with a backbone emerged from the water. The dinosaurs had their entire rise and fall, their 165 million years of absolute dominance over the terrestrial world, before the end Cretaceous event cleared space for the small mammals from which everything that came after, including the primates, including the hominids, including the people who invented calendars and then used them to think about time, eventually descended. All of this can be held at once if held loosely. It is not necessary to feel the full weight of 5 billion years in order to let the fact of it settle into the background of a quieter sense of things. The Earth is old, the Sun is older, the universe is older still. Against that background, the history of everything human is very new, new enough that in deep geological time it barely registers as a layer in the rock. And yet the rock also shows, if read carefully, the entire story of how new things arise from old ones, how simple chemistry becomes complex molecules, how molecules become self-replicating structures, how those structures eventually become organisms capable of developing eyes, and then hands, and then written language, and then the patience to sit alone with a piece of ancient meteorite and measure it carefully enough to find out how long everything has been going on. Patterson's ultra clean laboratory, the one he had to build specifically to eliminate the lead contamination that was corrupting his readings, was itself a kind of monument to how hard it is to look backward accurately across very large distances of time. The past does not offer itself cleanly. It has to be coaxed out of whatever survived, and what survived is rarely the most obvious thing, and the tools for reading it have to be built from scratch and then made cleaner and more precise before the reading is trustworthy. Patterson spent years on those measurements. He was working at the edge of what the instruments of his era could do, which is to say, he was working at the edge of what human beings then knew how to measure, which is itself a position that recurs throughout the history of anyone who has ever tried to understand how old anything is. The zircon grain from the Jack Hills does not look like the oldest thing on Earth. There is nothing visible about it that distinguishes it from any other grain of sand on a mineral-rich beach. Its antiquity is entirely contained in its chemistry, in ratios that require sophisticated instruments and careful analysis to detect that a grain of sand could carry the signature of a world 4. 4 billion years in the past could have survived, intact, through everything has a quality that is not quite surprising once understood, but takes a moment to absorb properly. Zircon survives because it is chemically resistant. It does not dissolve easily. It does not react with the materials it moves through. When the rock that originally contained it weathers away, the zircon is released and moves with water and wind until it settles into new sediment, where it waits. It has been doing this, forming, surviving, being released, settling, since the early Earth, and the oldest grains carry within them isotopic ratios that can be read as clearly now as the day they formed. There is something in this that is simply factual, and also in a mild way remarkable, that time leaves records in chemistry, that the decay of unstable atoms into stable ones proceeds at rates constant enough to serve as clocks, and that those clocks have been running since before the Earth had a solid surface. The moon above the Jack Hills tonight, or any other night from any other place, formed from a collision older than the hills themselves. The hills exist because of everything that happened in the billions of years since that collision, including the slow drift of continents, the erosion of older mountains, the accumulation of sediment in which the ancient zircon grains rested and waited. Every layer of that history is legible to the right instruments. The rock keeps records the way the crystal does, not in language but in ratios, in structures, in the particular arrangement of atoms that encodes the conditions of the world at the moment they formed. The Theia impact, the formation of the moon, the settling of the early crust, the first appearance of liquid water on the surface, the first self-replicating molecules, the first organisms, the first multicellular life. All of these are moments in the same continuous story, each one following from the conditions established by the one before it, the whole sequence stretching back to the collapse of a cloud of gas and dust that became the sun and its planets 4-6 billion years ago. That cloud collapsed because something disturbed it, perhaps a nearby supernova sending a pressure wave through the interstellar medium, and that disturbance set in motion a sequence of events that included, eventually, the existence of someone able to wonder about the sequence. The vast majority of that sequence involved nothing that could wonder. Bacteria existed on this planet for more than 1 billion years before anything multicellular evolved from them. The oceans teemed with microscopic life For a billion years, organisms without nuclei, without specialized cells, without any complexity visible to the naked eye, while the continents above the waterline remained bare. There were no sounds on land that were not geological, no footprints, no shade from anything that grew. The wind moved across bare rock, and the whole surface of the planet turned slowly, day after day, under a sun that was measurably dimmer than it is now, in a sky whose atmospheric composition would have been unbreathable to any creature alive today. This is difficult to hold as a picture because it is not a picture of anything. It is the absence of almost everything familiar, extending across more than a billion years. But it is also the foundation of everything that came after. The oxygen that fills the modern atmosphere was produced by early photosynthetic bacteria, released as a byproduct of their metabolism over hundreds of millions of years, accumulating gradually until it reached concentrations that made complex multicellular life possible. The world was built from the bottom up by organisms too small to see, working over timescales too long to feel, and the result of their collective chemistry was the air that every subsequent animal, including every human being, breathed without knowing where it came from. By the time the Triassic period opened and the early dinosaurs began their ascent, the Earth had already been running for 4 billion years. Life had already been present for at least 5 billion of those years. The history of dinosaurs, that 165 to 175 million year span that seems so long when set against human history, was itself a relatively late development, arriving near the end of the geological story rather than at its beginning, inheriting a world that had been built and transformed by everything that preceded it. The Triassic was not the beginning of life on Earth. It was not even close to the beginning. Pressing further back along the timeline, past the first complex animals, past the first multicellular organisms, past the emergence of bacteria and archaea from the chemical soup of the early oceans, the mind eventually reaches the point where the geological record becomes sparse and the inferences become more cautious. The oldest definitive evidence of life on Earth dates to approximately 5 billion years ago in the form of fossilized microbial mats found in Western Australian rock. There are older possible traces, carbon signatures, structures in ancient sediment that could be biological in origin, but the 5 billion year mark is where the evidence becomes solid enough for consensus. Between that date and the formation of the Earth, roughly a billion years elapsed during which the planet cooled, its oceans accumulated, and chemistry of increasing complexity was underway in conditions that are still debated. Life did not wait long, in geological terms, to begin. The meteorite Patterson analyzed, the Canyon Diablo fragment that gave the solar system its age, was itself formed in the early solar system in the first few million years when the gas and dust of the original cloud were coalescing into solid bodies. Meteorites of this type are called chondrites, and they are among the most primitive solid objects in the solar system, chemically unchanged since the moment of their formation. The Canyon Diablo impactor that struck the Arizona desert was a piece of the early solar system traveling through space for 5 billion years before its orbit brought it into contact with Earth's surface. When it arrived, it was unchanged from its formation, not eroded, not metamorphosed, not altered by the kinds of geological processes that continuously rework the rock of a living planet. The crater it made is still there, a mile wide and 550 feet deep, and it gives the desert landscape a quality of evidence, a reminder written in rock that things arrive from outside and leave marks. Patterson's analysis of that meteorite combined with measurements of Earth rocks and the known rates of radioactive decay in uranium and lead, produced a number that has held up under every subsequent investigation. The 54 billion year age of the Earth is not an estimate in the way a weather forecast is an estimate. It is a measurement refined over decades by independent methods that have consistently converged on the same answer. The agreement of those methods is itself a kind of satisfaction, the same quiet satisfaction that comes from measuring the same distance twice by different routes and finding the numbers match. Deep time, once it is allowed to sit at a certain distance, has less of the quality of something vertiginous and more of the quality of something simply wide. The dates do not press, they do not demand to be felt in full. They constitute a background, enormous still, extending in both directions from any given moment, against which the particular events of any era can be understood as genuinely recent or genuinely old, as brief or as extended as they actually were, without distortion. The dinosaurs were here for a long time. The universe was underway for a long time before them. The Earth has been settling and turning for a long time since. All of it proceeds in the same direction. The cosmic calendar's final 10 seconds, the ones that contain all of recorded human history, are not diminished by what surrounds them. They are specified. They have a location in a sequence that was already underway long before they arrived, and that location is the very recent past, the freshest layer, the newest growth. Everything written, everything built, everything understood and named and passed on is part of a development so new that the geological record has barely registered it. And yet it is from within that new development that anyone looking backward is able to see the rest of it at all, to measure the zircon, to date the meteorite, to trace the moon's origin back to the debris of an impact 4 or 5 billion years gone. The geologist who collected the Jack Hill's zircon grain, the physicist who counted its atoms, the cosmologist who modeled the Theia impact, the geochemist who finally cleaned his laboratory thoroughly enough to measure the age of the solar system accurately. All of them were standing in those final 10 seconds of December 31st, looking back across the whole long year, which is the only direction anyone can look. And what they saw when they looked carefully enough was not a mystery, but a sequence, one thing following from another, across distances so large that any single life is too small to span them, but not too small to perceive them. Patterson's numbers settled in 1956, and the age of the Earth became available as a fact rather than an estimate. The Canyon Diablo meteorite returned to storage. The Jack Hill zircon grain was mounted in resin and measured and cataloged, and the Earth continued its orbit around the Sun, which continued its fusion, which continued as it had for 6 billion years, which will continue for approximately 5 billion more. The whole enormous engine running at the same steady rate, producing the light that falls on the surface of a planet that has been here long enough that even the oldest things on it are not quite old enough to remember the beginning. It is an unusual kind of comfort, knowing that the world has been underway for such a long time without needing to be observed or understood in order to continue. The bacteria were here before the dinosaurs. The zircon grain was here before the bacteria. The solar system was here before the grain. And somewhere in the enormous span of all that time, long after the early chaos settled into something stable and slow, life began, quietly, in water too small to see, and has been building toward complexity ever since, at a pace that makes even the longest human history feel like the very last thing that happened, the newest layer, still warm. In Sagan's compressed year, The pyramids appear with only seconds to spare. The printing press arrives in the final second. And then the last of that second passes, and the calendar turns, and the year that contained all of this, every star that formed and died, every ocean that accumulated, every creature that lived and went extinct, every mountain that rose and eroded, every moment of every era ends quietly, in the way that all things measured by time eventually do, in the ordinary way of things that have simply run their full length and come gently to rest. Michel Cifra descended into the Skarasan cavern on July 16th, 1962, carrying enough supplies for 2 months and leaving behind every clock, every watch, every window, and every sky. The cavern was in the French Alps, approximately 130 meters below the surface, and its temperature hovered just above freezing. He had a lamp, he had a sleeping bag, a folding cot, and a journal bound in red cloth. What he did not have was any way to measure the passage of time except by the rhythms of his own body, and those rhythms, it would turn out, were considerably less reliable than he had assumed. The silence underground is not like the silence of a quiet room. It has a particular density to it, a weight that comes not from sound being suppressed, but from the complete absence of any source that might produce it. No wind, no animals, no shift of light across a wall. The cavern offered nothing to mark one moment as different from the one before it, nothing to separate afternoon from evening or one day from the next. Cifre ate when he was hungry, slept when he was tired, and recorded what he believed to be the date each time he woke. When he was finally brought back to the surface, after what he judged to have been 34 days underground, his calendar showed that 63 days had actually passed. His internal clock had been running at roughly half the speed of external time, expanding each felt hour and each felt day, until the 2 months had folded themselves into something that felt, from the inside, like a little over one. What Cifra had stumbled into, alone and without intending to, was one of the more interesting qualities of human time perception, its dependence on the world outside the body. In the absence of light cues, social schedules, meals at regular hours, and the sound of other people moving through their days, the brain's sense of duration drifts free. It does not simply slow or speed uniformly. It wanders. Some days underground felt very long to Cifra, others compressed. What the body cannot do, it turns out, is run reliably in isolation. The mechanisms that ordinarily keep a person's inner clock synchronized to the outer world require, at minimum, the outer world. Research carried out around the same period by Jürgen Aschoff and Rutger Waver at the Max Planck Institute in Germany extended Cifra's accidental self-experiment into something more systematic. Volunteers were housed in an underground bunker complex near Munich, cut off from all natural light and all time cues, and observed over periods of weeks. Without exception, the volunteers' sleep-wake cycles drifted. They did not collapse into randomness. They settled consistently into a rhythm slightly longer than 24 hours, running on average somewhere between 24 and 25 hours per cycle. Left to itself, the human body does not want to keep a 24-hour day. It wants a day that is slightly longer, a preference built into the machinery itself, and it takes the full apparatus of sunrise and sunset, and meal times and alarm clocks, and the sound of traffic below the window to keep it pulled back into alignment with the world outside. This means that every morning, without noticing, something in the brain performs a small correction. The faint brightening of the sky through a curtain is enough to reset the biological clock by a few minutes. The smell of coffee, the particular sound of early quiet before the neighborhood begins to move. These things are working on the body's sense of time in ways the mind never directly registers. They are maintenance. They are the world reaching in and keeping the inner clock honest. In the Scarason cavern, with nothing reaching in, the clock was left to its own inclinations, and it wandered, and 63 days became 34. Cipher's experience is a particularly vivid instance of something that happens, in subtler forms, to most people throughout their lives. The relationship between experienced time and measured time is not fixed. It shifts with attention, with memory, with chemistry, with age. A person sitting in a featureless room watching a clock will find the minutes longer than the same minutes spent in conversation or absorbed in a problem. A week spent in a new city, with every day full of unfamiliar streets and unexpected meals, and the effort of navigating an unknown place, will feel at its end like considerably more time than a week spent at home in a familiar routine. This is not an illusion in the sense of being wrong. It is the brain accurately reporting something about its own processing, how much was taken in, how much had to be attended to, how densely the hours were filled with incoming information. The neurotransmitter dopamine is involved in this in a way that researchers have spent considerable effort tracing. Dopamine is associated with reward and with the anticipation of reward, and its role in regulating the brain's internal pacemaker is housed in a structure deep in the brain called the basal ganglia. When dopamine levels are elevated, as happens with certain drugs that enhance its availability, subjects consistently overestimate how much time has passed. An interval that lasted 3 minutes will be reported as having lasted 5 or 6. The internal pacemaker ticks faster, accumulating more subjective units of time per objective unit, and the felt experience of the interval expands. In the other direction, conditions that deplete dopamine, as Parkinson's disease does, produce the opposite effect. People living with Parkinson's tend to underestimate elapsed time, reporting shorter durations than the clock records. The same 3 minutes becomes 2. The internal pacemaker runs slow, and the world seems to move faster than it should, time slipping by with less friction than expected, less accumulation. What this suggests is that the feeling of time's speed is not a secondary experience layered on top of what actually happens. It is produced by chemistry, by the specific concentrations of specific molecules in specific brain regions, and it can be altered by anything that alters those concentrations. Caffeine does it. Anxiety does it. Fear does it in a particular and well-documented way that reveals something else entirely about how the brain handles time under pressure. The common belief, held with considerable conviction by people who have experienced it, is that during a serious accident or a moment of physical danger, time genuinely slows down, that the brain, confronted with a threat, shifts into a higher processing mode and begins to perceive the world in finer increments, like a film slowing from normal speed to a frame-by-frame crawl. This belief is widespread enough that it appears in dozens of first-person accounts of accidents, falls, and near collisions. People describe watching events unfold with a clarity and a slowness that felt in the moment, like something beyond ordinary experience, as though the world had stopped rushing and given them time to observe. The neuroscientist David Eagleman and his colleagues at Baylor College of Medicine decided in the mid-2000s to test this directly. The question was whether the brain actually processes information faster during extreme fear, or whether something else is responsible for the retrospective sense of expanded time. To test it, they needed a way to present information faster than the brain can normally process, and then see whether a state of extreme fear enabled subjects to process it. They chose a perceptual speed reading display, a device worn on the wrist called a perceptual chronometer that flashed numbers at a rate just above the threshold of normal conscious perception. If the brain genuinely sped up during fear, subjects should be able to read the numbers. If it did not, they would remain illegible regardless of the subject's emotional state. The subjects were dropped from a 150-foot platform into a net below, a controlled freefall that, while safe, produced genuine fear responses documented across all participants. During the fall, every subject had the wrist display running. After the fall, every subject was asked whether they had been able to read the numbers. None of them had. The numbers moved too fast for the brain to register in exactly the way they moved too fast for the brain to register at ground level in a state of ordinary calm. The brain had not sped up. It had not shifted into any higher processing mode. What had happened instead was something more interesting and more subtle. The amygdala, a small almond-shaped structure embedded in the brain's temporal lobe, responds to threat by signaling the rest of the brain to encode memory more densely. Under ordinary circumstances, the brain records experience at a certain resolution, storing the broad outlines of events and dropping many of the details. Under threat, the amygdala's alarm signal causes the brain to record at higher resolution, saving more detail, writing the memory faster and more completely. When that memory is later retrieved, when the person recalls the fall, the brain reads back a denser, more detailed record than usual and interprets that density as duration. A recording that contains more information feels, when played back, as though it took longer to generate. The moment did not slow down. The memory of it is simply heavier than memories usually are, and that weight is interpreted as time. The felt slowing of a frightening moment is, by this account, a retrospective experience. It is something that happens in memory, not in the moment itself. The fall lasted exactly as long as it lasted. The sense that it lasted longer arrives afterward, in the replaying, in the brain encountering the unusual richness of what it managed to save. It is a memory illusion, not in the sense of being a distortion of truth, but in the sense of being a property of memory rather than of the moment remembered. This quality of memory, its ability to make intervals feel longer or shorter depending on how much was recorded in them, is part of what underlies one of the more persistent puzzles of experienced time. The way years seem to shorten as a person ages. The question of why summers felt longer at 7 than they do at 40 is one that most people encounter at some point without ever quite resolving. The proportional theory, developed and tested in part by the psychologist William Friedman, offers one of the more convincing answers. The central idea is straightforward once stated. Each year of life represents a fraction of the total life lived so far. To a 5-year-old, a single year is 1/5 of everything, 20% of the entire experienced world, a massive slice of all the time there has been. To a 50-year-old, the same 12 months is 1/50th of everything, 2%, a thin additional layer added to an already deep stack. The year itself has not changed. What has changed is the denominator. The year is being measured unconsciously against the total volume of time already experienced, and as that volume grows, the year's proportional weight shrinks. Friedman's research confirmed something that goes along with this. Older adults consistently recall recent events as having occurred further in the past than they actually did. Asked when something happened, a news event, a personal milestone, a trip taken, older subjects pushed the event back in time more than younger subjects did. The memory feels older than it is. This phenomenon, sometimes called forward telescoping in reverse, suggests that the brain's sense of the recency of an event is calibrated partly by how many other events have been laid down since it occurred. In a life with a long history behind it, even recent memories are surrounded by a great deal of other experience, and that density makes them feel more distant than they are. The summer that felt endless at 7 was full of firsts, first encounters with particular games, particular places, particular combinations of weather and company, and discovered freedom. Each day had a high probability of containing something that had never happened before, and the brain encountering novelty, recorded densely. The summer at 40 is spent in a largely familiar world. The days are competent and often pleasant, but many of them offer little that the brain has not encountered before in some form, and so they are recorded at lower resolution, their details released more readily, their shape compressed in memory to something smaller than the calendar measured. The summer has not shortened. The recording of it has. All of this points to something that does not immediately seem like good news, but turns out to be something closer to an invitation. The density of time, how long a period will feel, how much weight it will carry in memory, is partly a function of how much in it is new. A month in a new city, learning a language not previously known, navigating streets that offer no automatic pilot, trying food that has no familiar associations, will leave a memory considerably heavier than a month spent in established routine. The brain will later read that month back as having been long, full, rich with time. The route home from a new place always feels shorter than the route there, because the brain, on the way back, is no longer writing every intersection into memory. It already has them. The outward journey was full of encoding. The return is full of retrieval. There is a related finding in behavioral research that touches on a different dimension of how people experience time's passage, not the length of intervals, but the way the mind carves a life into chapters. In a paper published in 2014 in the journal Management Science, researchers Hung-Chen Dai, Catherine Milkman, and Jason Reese described something they called the fresh start effect. The study examined gym attendance records, diet-related internet searches, and stock trading activity across large data sets spanning multiple years, looking for patterns tied to calendar events. What they found was consistent enough across all three domains to constitute a reliable phenomenon. People initiate new behaviors, exercise regimens, dietary changes, financial strategies, at disproportionately high rates at the beginnings of new years, the beginnings of new weeks, and in the days immediately following their own birthdays. The pattern holds even when the underlying conditions have not changed. The gym is the same gym. The equipment has not been updated. The person's fitness level has not shifted overnight. What has shifted is the person's relationship to their own history. The start of a new year, or a new week, or the day after a birthday functions as a psychological boundary, a line drawn across the continuous flow of time that allows a person to place everything that happened before it into a category called the past, a chapter that has closed, a version of themselves that they are no longer required to carry forward. On one side of the line is who they were. On the other side is who they might be. The boundary is, of course, entirely constructed. The calendar does not actually separate one human life from another. The person who woke on the 1st of January is the same person who went to sleep on the 31st of December, carrying the same history, the same joints, the same unfinished thoughts. And yet the mind finds the division meaningful enough to act on, and in sufficient numbers to show up clearly in national data sets. The researchers called it a temporal landmark, a point in the flow of time that the mind treats as structurally significant, a marker against which behavior can be reset. The birthday is a particularly interesting case because it is personally scaled. It marks not the new year for the world, but the new year for the individual, and carries an emotional weight that a generic Monday does not. The data showed that gym attendance spiked not just on New Year's Day, but on every Monday, on every first of the month, and with even more consistency on the day after a birthday than on any of those. The mind is, it seems, looking for places to begin again, and it finds them wherever the calendar offers something that can be read as a seam. This is not irrational. It is, in a way, the mind making practical use of a real property of its own architecture. The sense of a fresh start does change behavior, at least for a time. The question of how long the behavior change persists is another matter, and one the research addresses with rather more equivocation. But the finding itself is worth sitting with for a moment, because it reveals something about how the human mind relates to the passage of time that is neither delusion nor mere superstition. It is the mind actively shaping its experience of time's flow, creating structure where the underlying reality offers only continuation. The same mechanism appears in smaller, quieter forms throughout daily life. The moment when the dishes are done and the kitchen is clean functions as a kind of temporal boundary for some people, a reset point after which the evening can begin properly. The start of a new notebook, the first entry in a new journal, the first page of a book begun on a rainy afternoon. These all carry a small version of the same charge, the same faint sense that a line has been crossed and something fresh is now available. The mind keeps finding these places and treating them as meaningful, not because it has been instructed to, but because the architecture of human experience seems to require them. Time without structure is, as Sifra found out in the cave, deeply disorienting. The mind builds structure where it can and calls those structures mornings and Mondays and New Year's, and organizes its sense of who it is around them. There is something quiet and slightly generous in this, when it is held without judgment. The mind's capacity to perceive its own history as organized into chapters, the old version of oneself safely on the other side of a line, the new version just beginning, is not a trick it plays against itself. It is a way of living inside a continuous experience without being crushed by the weight of it. Every morning is on a small scale the same gift, the conviction that a beginning is available, that the day ahead is not simply more of the day behind. That conviction is, in the strictest sense, not entirely accurate, and it seems on the available evidence to be rather useful regardless. The question of how much of daily experience is shaped by these constructed frameworks is one that runs deeper than the behavioral research captures. The circadian rhythm itself, the rough 24-hour cycle of waking and sleeping that governs much of human physiology, is simultaneously a biological reality and something that must be maintained through negotiation with the external world. The body has the clock, but the world sets it. The light through the window in the morning, the darkness at night, the timing of meals and physical activity, these are not merely accompaniments to the circadian rhythm, but part of its ongoing calibration. A person who consistently goes to bed at different hours, eats at irregular times, and lives in artificial light around the clock will find their rhythm destabilized in ways that extend well beyond feeling tired. Mood, cognition, immune function, and metabolism all turn out to be governed partly by the same circadian machinery, and all suffer when the clock is asked to run without adequate reference points. This is the same principle Sifri illustrated in the Scarson Cavern, simply expressed in the everyday. The body wants to keep time, but it needs the world's help. The clock is internal and genuine, but it runs best when it is in conversation with the external cycle of light and dark and warmth and cold that has paced life on this planet for considerably longer than the human species has existed. The 2 to 25 hour natural drift discovered by Ashoff and Waver is not a flaw in the machinery. It is simply what the clock does when the external conversation is removed, and it is a quiet piece of evidence for how deeply embedded in the physical world the human sense of time actually is. The sensation of a day is a coherent unit with a beginning and a texture and an end is assembled from dozens of small cues that most people process without awareness. The particular quality of light at late afternoon, different from any other time of day in ways that are immediately recognizable, even without looking at a clock. The shift in the sounds of a neighborhood between early morning and mid-morning. The way the body's temperature and appetite and alertness move through their own rhythms across the hours. All of this is the world and the body in continuous communication, each telling the other what time it is, and the result is the felt experience of a day as something with shape, not simply a block of duration, not simply 86,400 seconds measured out in equal units, but a thing with a morning quality and an afternoon quality and an evening quality, each recognizable, each carrying its own emotional texture. That texture is one of the quieter gifts of having a body that keeps time, the mild restlessness of a late afternoon that is not quite finished, the particular ease of an early evening after a day that went well, the specific weight of a Sunday night, which exists in the felt experience of most people as something distinct from any other night of the week, a night that carries an awareness of time's passage that other nights do not, a night tinged with the ending of one chapter and the beginning of another. These are not objective properties of Sunday or late afternoon. They are the mind's contributions, the emotional coloring laid over the neutrally ticking hours by a brain that has learned to read time, not just as quantity, but as quality, not just as duration, but as texture. The dopamine research, the cave experiment, the freefall study, the proportional theory of aging years, the fresh start data. These different investigations are each looking at a different facet of the same fundamental thing, that time, as it is actually lived, is not a simple stream running at a constant speed past a fixed observer. It is something constructed, moment by moment and year by year, from the interaction between the body's internal machinery and the world outside the body. The construction is largely unconscious. It is usually seamless enough that it does not draw attention to itself, and it is, when examined closely, a surprisingly intricate piece of work. The 5-year-old and the 50-year-old sitting side by side watching the same hour pass are in some meaningful sense watching different things. The child's hour is enormous. It contains a large fraction of all the time the child has ever known, and the world within it is still full of things that have not yet been encountered before, and the brain is writing it all down. The adult's hour is smaller in felt terms, a thin new addition to a very large existing sum, and the brain, having seen most of what the world contains, records it with a lighter hand. When the hour ends, each will carry away a different memory of what just happened. Both will be accurate records of what their brain actually processed. Neither will be a complete account of the hour itself. That gap between the hour as it was and the hour as it is remembered is where most of experienced time actually lives. It is where Sifra's 63 days became 34, where the free fall stretched into a long, slow arc of detail that the clock did not confirm, where the gym fills up on January 1st and the child's summer spreads wide across the whole of July. The machinery that creates these experiences is not broken or mistaken. It is doing exactly what it evolved to do, managing a continuous stream of sensory information, filtering and compressing, and occasionally amplifying, and handing the result back to the person as the only experience of time they will ever directly know. Michel Sifra, when he finally came up out of the Skarasan cavern and stood again in August sunlight, was astonished, not distressed, according to his own accounts of the experience, astonished. He had expected to have spent a month underground, and found he had spent 2, and the gap between the number he had carried down into the dark and the number the calendar returned to him was not a source of loss, but of genuine wonder. He had gone looking for something about the nature of time, and he had found it in the place and the condition best suited to finding it, alone, underground, in the cold, without a clock, listening to a body that turned out to be telling a slightly different story than the world outside was telling. The quiet of a dark room at this hour is not so different in kind from the quiet of the cavern, not in degree, of course, not in its completeness, but in the general quality of the world, drawing back and leaving the body to its own rhythms. The sounds outside settle, the light is gone, the markers of hour and activity that organize the waking day grow soft and indistinct, and in that soft indistinction, the body's own clock, the one that runs a little long, when left entirely to itself, begins to take over, carrying forward toward sleep in the unhurried way that seems, in these conditions, to be its natural direction. The mind is drawn to beginnings. It finds them in the first of the year, and the first of the week, in the morning after a birthday, and the moment when the kitchen is finally clean. It finds them in the particular quality of late evening, when the day's chapter is closing and the night's chapter, the wordless one, is about to begin. That inclination toward the fresh edge, toward the new interval, toward the opening of a period that has not yet been written, is not a departure from the way time actually works. It is, in its way, a true response to something real, that time does keep offering new moments, that the next one has not yet arrived, and that the one after it has not either. The mind that reaches for beginnings is not deceiving itself. It is simply paying attention to the right thing at the right hour, which is the thing that has not happened yet, and the space that remains, and the long quiet that is already beginning. At the base of the Great Pyramid of Giza, the limestone casing stones were still intact. That is worth holding for a moment. Not the pyramid as it appears now, weathered and stripped to its stepped core of rougher rock, but as it stood in the 1st century BCE, its outer surface still smooth, still pale, still catching the morning light off the Nile with something close to a gleam. Cleopatra the 7th would have seen it that way. The geometry was still sharp at the edges. The capstone, or whatever had crowned it, was long gone by then, but the flanks still ran in clean planes from the desert floor upward to the open sky. And to stand at the base and look left and right along the lowest course of casing stones was to look at blocks of white limestone, each as tall as a door, fitted together with gaps no wider than a knife blade. She was not a tourist. She was a queen and a scholar and an administrator, and Egypt was her country in a very direct political sense, which meant that the pyramid was, in whatever complicated ceremonial and ancestral way, hers. But even for a woman who had been educated in 7 languages and had read widely in the library at Alexandria, the age of that structure would have been almost as resistant to comprehension as it is now. The Great Pyramid had been completed around 2560 BCE. Cleopatra was born around 69 BCE. That places roughly 2,500 years between her and the builders who had cut those stones, dragged them and lifted them into place, generation after generation of workers whose names are almost entirely unknown to us. 2,500 years is a long time. It is enough time for languages to become unrecognizable, for coastlines to shift, for cities to rise and be buried under the cities that replaced them. And yet Cleopatra was not standing at some enormous midpoint in history between the pyramid's construction and the present moment. The numbers do not work out that way. From the pyramid's completion to Cleopatra's birth is roughly 2,500 years. From Cleopatra's death in 30 BCE to the Apollo 11 moon landing in July of 1969 is roughly 2,000 years. She is, in that purely numerical sense, closer to the moment Neil Armstrong pressed his boot into the lunar surface than she is to the moment the last casing stone was laid. The stones beside her eye level still showed faint tool marks in places, shallow grooves where the surface had been dressed and smoothed. A workman's chisel had made those marks. The hand that held it had been a human hand, and the person attached to it had worked in the afternoon heat of the Nile Valley with water and bread and aching shoulders, and had left those thin parallel lines in the rock as the only record that he had ever existed. Cleopatra could have reached out and touched those marks. She was 2,500 years from the hand that made them, and the marks were still there. What that arrangement of numbers suggests is not simply that time is long. It suggests that the way time appears to arrange itself, with antiquity far behind and the recent past closer to hand, is something the mind imposes on a sequence that has no such gradient built into it. The pyramid is old in relation to Cleopatra. Cleopatra is old in relation to us. But none of those things are old in relation to the limestone itself, which had been forming in a shallow sea somewhere around 50 million years before anyone quarried it. The word antiquity is elastic in this way. It stretches in different directions depending on where the measurer stands. On December 17, 1903, on a stretch of sandy beach near Kitty Hawk, North Carolina, a 12-horsepower gasoline engine turned two wooden propellers mounted behind two cloth and spruce wings, and a biplane weighing around 600 pounds lifted off the ground. The flight lasted 12 seconds and covered 852 feet. Orville Wright was lying prone on the lower wing, controlling the craft. His brother Wilbur ran alongside on the ground for the first few steps and then stopped, watching it go. They made 4 flights that day. The longest covered about 852 feet at its best measurement. The aircraft, by the end of the day, had flown a total distance that a brisk walker could cover in roughly 3 minutes. 66 years later, on July 20th, 1969, Neil Armstrong climbed down a ladder from the lunar module Eagle and placed his left boot on the surface of the moon. The moon is, on average, approximately 238,855 miles from Earth. The entire distance traveled by the Wright Flyer on its first day of powered flight was 852 feet, roughly a sixth of a mile. The Apollo 11 mission traveled a distance approximately 1.5 billion times farther than that. 66 years. That is a single human lifetime. There are people who were adults when the Wright brothers flew at Kitty Hawk, and who were alive to watch the moon landing on a television screen. The same set of years that contained both events also contained, in between them, the invention of commercial radio, the First World War, sound cinema, the Great Depression, commercial aviation for paying passengers, the Second World War, the hydrogen bomb, the first satellites, the first animals in orbit, and the first human beings in space. The pace at which those 66 years moved through their content seems, in retrospect, almost difficult to sustain. But the gap itself, the specific measurement of 66 years between a machine that flew the length of a modest garden and a machine that landed human beings on another world, has a quality that numbers rarely capture on their own. 12 seconds in the air at Kitty Hawk, 4 days of transit to the moon. The thread between those two events is unbroken. It ran through the same continuous movement of days that anyone alive in 1903 was already living inside, and anyone alive in 1969 had simply continued along. Wilbur Wright died in 1912, before the First World War had ended. He did not see any of it. But Orville Wright lived until January of 1948, long enough to see the jet age beginning, long enough to know that the thing they had built on that beach had become something that would continue well past the point where he could follow it. The distance between the Wright Flyer and the lunar module is not really a technological distance, though it is that too. It is a distance between two versions of what human beings believed was possible, and the 66 years in between is the time it took for the second version to arrive. On Wrangel Island, in the Arctic Ocean north of the Siberian coast, the ground is cold for most of the year and open in ways that most land is not. Flat tundra, low vegetation, the sound of wind over water not far in any direction. The island is not large. It sits alone in the sea, separated from the mainland by a stretch of water shallow enough that during periods of lower sea level it was connected to the continent by dry land. At some point after the sea levels rose and that connection was severed, a population of woolly mammoths found itself isolated on the island. The mainland mammoths were already gone by then. The great herds that had moved across Siberia and North America and Europe had declined and disappeared, the last of them probably dying out on the continent somewhere around 10,000 years ago. The reasons are not entirely settled. The climate was changing and human hunters were moving into new territories, and the combination of those two pressures appears to have been more than the mainland populations could sustain. But on Wrangel Island, cut off from both the climate shifts and the hunters, a small population survived. They were smaller than their mainland relatives. Island isolation tends over generations to reduce the body size of large mammals when food becomes a limiting factor, and their range was constrained by the island's edges. They lived there for thousands of years after the last mainland mammoth had died. The most recent evidence from Wrangel Island places the final extinction of that isolated population at approximately 1650 BCE, give or take a few centuries, which means that when the Great Pyramid of Giza was being sealed and consecrated around 2560 BCE, there were still woolly mammoths alive on Wrangel Island. They would continue to exist for nearly another 1,000 years after the pyramid was finished. Khufu's tomb was complete. The casing stones were laid. The workers had dispersed. And somewhere in the Arctic, a small herd of diminutive woolly mammoths was moving across the tundra, breathing cold air, cropping the low grass with their curved tusks, entirely unaware that they were the last of anything. The word prehistoric carries with it a certain quality of distance, a sense of the ancient and the gone, a world separated from recorded human activity by some large and clear divide. But the mammoths of Wrangel Island were not prehistoric in that clean sense. They overlapped with the Bronze Age. They were alive while the Akkadian Empire was functioning, while the cities of the Indus Valley were still trading, while the Shang dynasty in China was keeping records. The world they lived in was, in many places, a world of writing and administration and organized religion. The tundra grass bent under their feet. Their breath was visible in the cold air. They were simply on an island, and no one who was keeping records knew they were there. The first students at Oxford did not think of themselves as attending a university. The word university, in its formal institutional sense, was still taking shape in the late 11th and early 12th centuries, and the community of scholars that gathered in Oxford had grown up around the practice of teaching rather than around any single founding charter or decree. Teaching at Oxford is documented from at least 1096 CE. What that teaching looked like in those early years was probably informal by later standards. Scholars drawing students to particular rooms or halls, instruction in Latin, the material drawn from manuscripts copied out by hand in monasteries across Europe. The buildings were stone and candlelit. Books were objects of considerable value and effort, each page the result of hours of careful work. By the time that community of scholars had been functioning for roughly 3 centuries, by the early 1400s, it had grown into something recognizable as an institution with colleges and statutes and a long institutional memory of its own. The teaching had not stopped in those 300 years. The library had grown. The students had come and gone, and many of them had died and been replaced by other students, and the whole thing had persisted through plague and political upheaval and several complete changes in who held the English crown. The Aztec Empire was founded in 1428 CE. The date is specific and meaningful. It marks the formation of the Triple Alliance between the city-states of Tenochtitlan, Texcoco, and Tlacopan, the political arrangement that would, over the following century, expand into the dominant power of central Mexico. By 1428, Tenochtitlan was already a functioning city, built on an island in Lake Texcoco, with causeways connecting it to the shore and markets drawing traders from across the region. But the empire, in its formal political sense, began there in that year. Oxford had been operating as a place of continuous teaching and learning for more than 330 years before the Aztec Empire existed. The scholars in those early Oxford lecture halls were alive in a world that included the Norman conquest of England, the First Crusade, the construction of Notre Dame de Paris, the Magna Carta, the Black Death, the 100 Years' War. All of that came and went within Oxford's institutional lifespan before Tenochtitlan built its first great temple. Neither fact diminishes the other. The point is not precedence. The point is the way familiar timelines, when held against each other, reveal themselves to be far less synchronized than they seem. The medieval feels like one world, the Aztec feels like another, but they overlapped substantially, and the overlap lasted for centuries, The Oxford Lecture Hall in 1096, stone walls and candlelight, and a scholar reading aloud from a manuscript that had been copied by a monk in a scriptorium somewhere, that room was real. The students in it were cold in winter, and warm in summer, and hungry at the wrong times, and occasionally brilliant, and frequently ordinary. The city of Tenochtitlan, with its floating gardens and its causeways, and its ceremonial center rising above the lake, was also real, and it would be real for 300 and more years before the two worlds had any documented encounter with each other. 300 years of an institution existing before the empire, most associated in Western imagination with that same historical period, had even begun. Albert Wolson was born in 1850 and died on August 2, 1956, at the age of 106. He had served as a drummer boy in the Union Army during the American Civil War, enlisting in 1864 at the age of 14. By the time of his death, he was the last verified surviving Union veteran of that war. The last one. Every other man who had worn Union blue, who had drilled and marched and camped and fought or waited in the long months between fighting, every one of them had died before August of 1956, and Wolson was what remained. The Civil War belonged to a world of things that now seem very distant. Dispatch riders on horseback, supply wagons pulled by mules, field surgeons working in tents, soldiers communicating by telegraph when they could, and by courier when they could not. The weapons were rifled muskets and artillery and cavalry charges. The logistics were enormous and slow and dependent on rail lines that could be torn up and on rivers that could be blocked and on weather in ways that modern military operations are not. The photographs from that war are in black and white, formal, and posed in the way that long exposure times required. The soldiers looking at the camera with the particular stillness that was not composure, but necessity. In 1952, 4 years before Albert Wilson died, the British Overseas Airways Corporation, BOEC, inaugurated the world's first commercial jet passenger service using the de Havilland Comet. The Comet was a pressurized jet aircraft. It carried passengers in a cabin at altitude, above weather systems, crossing distances in hours that propeller aircraft had taken many more hours to cover. The experience of being inside it was fundamentally different from anything that had preceded it. Quiet by the standards of piston-engine aircraft, fast, high, the world below visible as a curved surface when the weather was clear enough. Albert Wilson, the last survivor of the American Civil War, was alive when those jets entered service. He was 102 years old, and somewhere in Minnesota, he existed in the same continuous present as BOAC's Comet passengers, crossing the Atlantic in pressurized comfort. The era of horse-drawn supply wagons and battlefield telegraphs and 4-day marches through Virginia mud was not a different world. It was, measured in human lifespans, not even a different life. The Civil War ended in April of 1865. The first commercial jet service began in 1952. Between those two dates, 87 years, less than a century. The telegraph became the telephone, became the radio, became the radar, became the jet engine, and every step in that sequence was made by people who had been born into the previous step. What Wilson's lifespan contains is not unusual in one sense. Any life long enough will span extraordinary changes. But his particular span has a quality of apparent impossibility about it, because the two worlds it brackets, the world of the Civil War and the world of commercial jet aviation, seem to belong to different centuries of human development, separated by some enormous gap of time and ingenuity. They are not. They are separated by a single long human life, and the man who closed that gap sat in Minnesota in the summer of 1956 and breathed the same July air as everyone else. He died on a Tuesday. The jets continued flying. These distances accumulate in ways that resist ordinary arithmetic. Cleopatra looking up at the pyramid, the Wright Flyer lifting from the sand, the dwarf mammoths on their Arctic island, the Oxford scholars in their candlelit hall, Albert Wilson drumming in the Civil War, and then outliving the age of piston engines. Each of these sits at a particular point in the sequence of years, and the sequence is continuous. No gaps, no missing segments, just one day after another, all the way along. The thing that makes these juxtapositions feel implausible is not the facts themselves. The facts are straightforward and documented, and individually not difficult to hold. It is the combination of them that produces the specific sensation of temporal dislocation, the feeling that time, which moves at a perfectly steady rate and has no texture of its own, has somehow arranged itself into shapes that should not fit together. Cleopatra closer to the moon landing than to the pyramid she could touch. That is a fact about numbers. It does not require any physical explanation. The numbers simply work out that way because 2,500 years and 2,000 years are both very large quantities, and the difference between them from the inside of a single life is not immediately legible. The Wright Flyer covering 852 feet and the Apollo spacecraft covering a distance 1 5 billion times greater, with only 66 years of continuous human work between them. That is a fact about the pace of accumulated knowledge when it is moving quickly. It does not feel like 66 years from the inside of the achievement. It feels, in retrospect, like something that should have taken longer. The mammoths on Rangel Island, still alive while the Bronze Age went about its work to the south. That is a fact about geography and isolation, about what can survive when the pressures that ended the mainland populations do not reach a particular island at the right time. The mammoths on the island were not aware of being remarkable survivors. They were simply where they were, in the cold, cropping the grass. There is something in the arrangement of all these facts that is not about any single one of them. It is about the way time, which we live inside without being able to see its shape from outside, turns out to contain arrangements that surprise us when we look carefully at where things actually fall. The pyramid at Giza did not change its position in time when someone calculated that Cleopatra was closer to Armstrong than to Khufu. The calculation simply made the arrangement visible in a way it had not been before. The numbers had always been what they were. The surprise is not in the facts. It is in the habit of mind that places ancient things in a uniformly remote past and recent things in a uniformly close present, as if time were a gradient rather than a sequence. Oxford's founding and the Aztec Empire's founding are separated by more than 330 years, and they still feel, to a mind that has not done the arithmetic, like they should belong to approximately the same era. Medieval and pre-Columbian, both far back, both in a part of the past that seems generally distant and unified. But 330 years is not a small number. It is the distance between the founding of the Aztec Empire and the end of the American Revolution, with decades to spare. The mind does not hold all of history in a single flat plane, equally accessible and precisely spaced. It holds it in clusters, organized by familiarity and by the stories it has been told. And those clusters can overlap in time in ways that the stories do not always make clear. The mammoths and the Bronze Age. That is perhaps the clearest version of this. The woolly mammoth is a creature of ice ages, of Pleistocene megafauna, of a world that predates the historical period in most imaginations. And yet on Wrangel Island, in 1650 BCE, they were still there. The Bronze Age was not a period after the mammoths. It was a period during them, for anyone standing in the right place. The cold grass of Wrangel Island bends under the wind in the same way it has always bent. The island sits in the Arctic Ocean the same way it has always sat. The water around it is the same water, the same cold gray-green, the same low waves moving across it, and the same wind that has come down from the north for thousands of years. There are facts about Albert Wilson that are not in the record, what he thought about in the summer of 1956, when he was the last of the men who had served in that war. Whether the distance between 1864 and 1956 felt long to him, or simply like the accumulation of ordinary days. Whether the jet aircraft that flew over Minnesota seemed to him like a logical continuation of everything that had come before, or whether they seemed like something from a different world entirely. The record stops at the documented facts of his life, and what the inside of that lifespan felt like is not available. What is available is the exterior measurement, 1850 to 1956, 106 years, from a world lit by candles and oil lamps and the particular orange glow of campfires on the Virginia hills to a world in which pressurized aluminum tubes were carrying passengers above the weather at speeds that the entire Union Army combined could not have imagined. He was born into one of those worlds and died in the other, and between them he had simply continued being alive, one day at a time, the way everyone does. The distance between things that seem fixed in separate eras is almost always shorter than it appears. The distance between things that seem recent is almost always longer. Both of these tendencies are features of the same mental habit, the organization of the past into a story with chapters, when the past was actually just the continuous movement of time through specific places and specific lives without pause or chapter break. Cleopatra standing at the limestone base of the pyramid, the casing stones pale and gleaming in the morning light, looking up at something that was already 2,500 years old. She was not standing at the beginning of history. She was standing somewhere in the middle of a sequence that had been running for a very long time already and would continue for a very long time after her. The pyramid behind her was old. The civilization that built it was ancient even to her. And still, the moon landing was closer to her in raw years than the morning when the last block was laid. The Wright Flyer's engine turned its wooden propellers in the cool December air off the North Carolina coast, and the machine lifted, and 12 seconds later it came back down to the sand, and Orville and Wilbur Wright looked at each other on a beach that was otherwise almost empty. They sent a telegram to their sister in Dayton, success 4 flights, Thursday morning, all against 21-mile winds started from level with engine power alone, average speed through air, 31 miles longest 57 seconds, inform press home. Christmas, the press was not, initially, very interested. The telegram arrived. The local newspaper editor was told. He ran a small item that got the details wrong. The world did not immediately understand what had happened on that beach. It took some years for the significance to become clear to the people who had not been there. By the time it was clear, the men who had been there were already different ages, and the world had already changed in ways that would make the next change easier, and then the next one after that. 66 years of that accumulation, and then the moon. The island of Wrangel sits at roughly 71 degrees north latitude, above the Arctic Circle in the Chukchi Sea. In winter, the sun does not rise above the horizon at all. In summer, it does not set. The mammoths that lived there in the last centuries of their existence would have known both the long dark winter and the long pale summer. The ice at the edges of the island freezing and releasing with the seasons. They were not large mammoths by the standards of their extinct mainland relatives. Isolation and the finite resources of an island had over generations reduced their scale, but they were still mammoths, still recognizably the same creature that had crossed the land bridge from Asia into North America thousands of years before, still carrying the long curved tusks and the thick coat that the species had developed across the long cold centuries of the Pleistocene. When the last of them died, the last individual in the last small herd on that cold flat island in the Arctic, there was no one there to record it. The extinction happened without a document. The date, 1650 BCE, approximate, comes from radiocarbon analysis of bones found on the island centuries later. What the last day of their presence on the island looked like is not in the record. Whether it was summer or winter, whether the herd was small by then, reduced to a few individuals, or whether the final collapse was more sudden than gradual, whether there were calves. The cold grass on Wrangel Island grows the same way it has always grown. The wind moves across it the same way. The Arctic terns that nest there in summer arrive on the same schedule they have always kept. The island does not carry any visible mark of what it once held. It is just the island, cold and flat, and open to the sky, and the water around it is the same cold water. Somewhere in the middle of the Bronze Age, while the civilizations of the Eastern Mediterranean were keeping records and building temples and sending ships out from harbors that are still there, overlaid with later centuries, the last woolly mammoths were alive, still moving, still breathing the cold Arctic air, the tundra bending under their feet one last time before the silence closed over the island, and the record of them became only what could be found in the ground. The grass was still there afterward,